Hello, welcome to this lecture on the final lecture, hopefully on LDPC decoding, where we will convert the code to fixed point real quick and then do the offset Minsum, and that will close. Okay. So, to convert to fixed point, we need a few sort of settings. First is what is the maximum received value you want to look at. So, when you do fixed point, you should also fix the window. Usually, I take it as 3 or 4. You can play around with this and see how it goes. That is one, and then the next one is the setting of the number of bits. Okay, so up to 4, but how many bits? So one way in which I like to do this is to set something called max int, max of the maximum quantized value that you want to have. So maybe we will call it max quantized r. So you can have that as 31, for instance, right? So 31 means so this is not going to exceed 31 at all, the quantized received value. So these are two settings that I use, and then once you do that, you have to now, once r comes in and you've done the puncturing for the message part, you have to do the quantization. So how do you do the quantization? It's quite easy. So r quantized equals floor of r by r max multiplied by max qr. Okay. So, I am simply dividing by the maximum possible r max that I want to have, and then multiplying by max qr and flooring. So, this will convert to integer and all that, but then except that r may have gone greater than r max. So, what I do for that is rq of rq greater than r max equals r max, right, and then rq of rq less than minus r max. It can also go in the other direction, and that I will set as minus r max, not r max, I am sorry, max qr, minus max qr. Okay. So, this is the simple quantization and clipping also that is done. So, at the end of this, I have integer values for rq, and if it is greater than, I am sorry, so I should be careful here. This is also max qr, this is also minus max qr. So, if it has exceeded max qr on either side, I simply set it to that value. So, this gives me integer values the receiver, and this L is going to be rq. Okay. So, this is just one very quick way to deal with the quantization, number one. This will result in some suboptimal performance, right. So, there will be a lot of values which you are dealing with as real numbers, but now they have become quantized. So, that is one thing. And then after that, there is really very little change that you have to do. Okay. So, a few changes that you have to be careful about is first this L. Okay. So, this L is set as rq now. Okay. And then as you see in this iteration, the L value of L grows. Okay. And then there is also this minus negative sign that I am doing for r and L. Okay. So, you have to be slightly careful when you quantize these things, so that things do not blow up and still the calculation is done in a reasonable way. Okay. So, some of the things one needs to pay attention to is how much will you let L grow and how much will you let R grow. Okay. So, because remember, even R is a value here, right. So, R is stored here. So, you will have to keep limiting both L and R to some reasonable range. Okay. So, one needs to pay some attention here. So, it is not just easy to quantize the R and let it run, because the other values also you have to quantize, you have to fix the bit width in some sense. Okay. So, maybe we should just try running this for a while to see if this is affected any of the performance. I will run it for 10 blocks and see what happens. Okay. So, you see you are getting some errors, so maybe you can go to a larger SNR. Okay. So, you are getting a lot of errors here. Okay. So, you see even at high SNRs the errors do not go down. Okay. So, the quantization seems to be hurting you in some way, but one needs to be also be careful about how we have done the quantization. We just limited it, but then we are not limiting the other values carefully. So, maybe it is good to check if RQ happened properly or not. So, this will all be 0. Okay. So, we go to 33:64. Okay. So, it seems to be doing okay here. The quantization has sort of worked okay. So, maybe we need to do more iterations. 8 is too much. 2 less, maybe we will do 20 iterations. Let us run at 4 dB. So, we should see some. Okay, so, it's still getting 10 errors. I am not very happy about it. Okay. All right. So, so to account for the increase in the value of L in your inside your decoder. So, usually the L value. So, you should, if you cut off the R and the capital R and the storage for the row at 31. So, that is just 5 bits that we are using here. So, it is good to use more value here. So, usually most people use 2 bits more for the L value 127, and then one needs to look at the cutoff closely here. So, once again here, so if you remember max QR was 31, so you can limit it to 31. So, here I think if it is less than, so usually since it is 2's complement, one can do this light little trick here, so that it goes up to minus 32 and plus 31. Okay. So, that is the range for the RQ here. L is RQ, but remember L is going to be allowed to grow up to 127. Okay. So, minus 128 to plus 127. So, that is something that one needs to be careful about here. So, the L subtraction is happening fine, but when this T-reg happens, okay, so I do not want to store more than 5 bits here. Okay. So, remember L was L, I am going to allow it to grow up to 127. Okay. So, when I do the subtraction, after I subtract, I have to further make sure that what I store in T-reg is only 5 bits long. Okay. So, I mean 6 bits, 6 bits total, including one sign bit. So, it should go up only up to minus 31 to plus 31. So, that is an adjustment that one needs to make. So, after I am done with this, I should make sure that happens. So, if so one quick way of doing it is T-reg of Ti comma T-reg of Ti comma colon greater than max QR, right, equals max QR. Okay. So, if it exceeds, you do that, and then if it goes lesser, okay, less than, if you remember, minus max QR plus 1, then you set it as minus max QR plus 1. Okay. So, this is a way in which I ensure that my T-reg value does not exceed the 6 bit limit, minus 32 to plus 31. Okay. So, that is where the range of T-reg lies. After that, I do this, and then I want to do an offset minsum here. So, maybe I will set up that offset also. Offset, maybe we will set it as 2. Okay. So, 2 may be okay. So, the offset, it is convenient to set it in min. Okay. So, min 1 and min 2 are the ones that need to be offset. So, what you can do is if min 1 greater than offset. Okay. So, this is a check you have to do. Min 1 is min 1 minus offset. Okay. So, this you can end, and then the same thing for min 2 as well. Okay. So, slightly better way to do it is the following. I am sorry. So, you do the subtraction first, okay, and then you see if it is less than 0, and you set it to 0. Okay. So, same thing for min 2 as well. Yeah, this is better. This is the more cleaner way to implement the offset. Okay. So, like I said, this is a way in which minsum can be made slightly more accurate. So, you introduce the offset here, you subtract the offset, and if the min 1 has gone negative because of that, you set it to 0. Same thing with min 2, and if min 2 has gone less than 0, you set min 2 to 0. That is it. So, after that, nothing else changes as far as the parity is concerned. And then when you add L here, okay, so this you have to check if because I am adding here, right. So, I am adding some value to L, and you have to check if it has gone greater than max QL. Okay. See, max QL was 127, I do not want L to exceed 127 either. Okay. So, I am going to check if L has exceeded that, and for that one needs to do the same sort of adjustment here, which is a little bit more painful. So, what one can do here is the following. Okay. So, instead of assigning it like this, I will assign it to temp here, and this I will take as temp, okay, add it up. So, this temporary storage will be slightly larger, and then I do temp of temp greater than max QL to be equal to max QL, and temp of temp less than minus max QL plus 1 to be equal to minus max QL plus 1. So, this makes sure that the range of L is not violated, and then I store it in temp. I can do in fact something like this in treg here also. Instead of storing this in treg, I can do temp here and simply do everything with temp and finally assign it to temp. That is also I think is a good idea instead of doing this massive exchange here. So, let me just do that off carefully. So, I will assign it to temp and say temp of temp. And even here, this is better. This looks cleaner code, so that works out better for us. And then finally, treg of I believe ti comma colon equals temp. Okay, so this is sort of slightly clean. So, I do the fixed point manipulation with the temporary storage here, some register or something which may be slightly larger, and then you finally quantize it down and store it in treg. Okay, so this is sort of clean. Same thing I did here for L as well. I first did the addition into some temporary thing. So, up to now it could be a little bit bigger, and then I cut it down and then store it in temp again. Okay. So, other than that, I do not think you need to do any other change. This should work just like that, 20 iterations, maybe that is a good idea. So, maybe it is good to check a few iterations and see how this value works out. Okay. So, maybe I will stop somewhere here. This is a good place to stop, set up a breakpoint, okay, and then let us just run, see if this is running. Okay, it seems to be running. Maybe clear the whole thing up. So, let us see RQ of 1:32, this will be all 0 because I am puncturing this. So, if you look at 33:64, the next two blocks, you see a lot of values, and it goes from minus 31 to plus 30, minus 32 to plus 31 the way I have seen it. One can do max of RQ just to check, it has gone up to 26, min of RQ has gone up to minus 11. So, that is the range of max. So, you expect more positive values than negative values, that is good. Okay. So, now what about L? So, if you see actually L of 1:32 in the first iteration will still be 0, nothing would have been corrected in the first iteration because it got assigned as 0, nothing really flows. You will see in the third iteration onwards you will start seeing some values here, but if you see L of 33:64, something will be different. Okay. So, you can see RQ, we saw this just before. Okay. So, is everything exactly the same? That is not very good news. So, maybe okay, it looks to be equal for now. So, maybe that is just the first iteration, and that block does not get corrected. Let us say the next iteration. Continue. Let us try L. It's still not changing. Next iteration. Hopefully, something should start flowing now. One important thing about puncturing is when you set R to be equal to 0, your RQ will also end up being 0, but then MATLAB's sine function treats 0 as 0. So, for instance, if you look at what MATLAB's sine function does, it does sine of 0, it gives a 0. Okay. So, that is actually not a very good way in my opinion to implement the sine function. So, when you do that and when you do product of sine, everything will go for a toss. So, a better thing to do is to do something like this, to implement your own sine function and put a greater than or equal to 0 here. Okay. So, if you do this, then things work out quite okay. Okay. So, the sines, instead of relying on MATLAB sine function, you do 2 into the value you want greater than or equal to 0. So, if it is equal to 0, I am going to assign plus 1 in the sign. Okay. So, this is an important change that one needs to make sure things work, particularly in the punctured case and the quantized case when you may have things equal to 0. Otherwise, everything will keep on being 0 all the time. None of the rows will effectively be there. Okay, so this is one of the bugs that you need to correct when you quantize. Okay, so I think with this most of the things are done. So let me just ensure that one little detail I've taken care of carefully. And then I've done this. I think this looks okay to me. So let's run this. We'll keep a breakpoint here and see if everything is working correctly or not, and then we can run this. Okay, so once again I'm running at a high enough EB over N naught, so let's run. Okay, so if you run this, you can see RQ, which is the quantized R from 1:32 is 0, and RQ from 33:64 is some value. There are some negatives here, -5, 1, but other values are okay. And if you look at L of 33:64, you should see some change here. Yeah, some of the values have gone up, the minus has become plus, the -1 has become 0. So some in the positive direction. But interestingly, if you look at L of 1:32, okay, so this has some values as well. So those values have also been corrected, and you're getting some changes here. Okay, so this is what will happen when you do it. And if you continue the iteration, the L will change again. Remember, this was quantized and it's all becoming very, very large. Okay, and if you look at this value also, it's also becoming very large, and quickly one is converging to the correct answer. Okay, so this is something that one can see. Maybe I can quit the debugging here, clear the breakpoint, and then run it for some time and see how it happens. So maybe we'll run it at 2 dB EB over N naught. Okay, this is rate 1/3. This is quantized. It's quite a low block length. Let's run it and see what happens. Okay, so no errors at 0 dB, and then maybe run for 100 blocks just to be sure. At 2 dB EB over N naught, rate was 1/3. This is the quantized decoder, and you can see even the quantized decoder works very well and gives you no errors at 2 dB EB over N naught. Okay, so hopefully this is clean now. I have not made any other change. This is a clean decoder. So you can see the offset also plays a very good role in improving the error rate. So 1 out of 100 was an error at an EB over N naught of 2 dB. You can even reduce the EB over N naught if you like. Remember, this is just a block length of 1000. So if you look at K, N is just 1000, rate will be 1/3. Okay, so because I did that, and so this is easy enough to do. You can even reduce the bit error rate, the EB over N naught further, and so you'll see more errors will start creeping in. So at this point it was just 10 power minus 2, 1 out of 100 were an error. If you go to 0 dB, you will get more errors at these block lengths, and but the whole decoder is working sort of reasonably. We've incorporated most details that need to be there. The puncturing of the first part, we didn't incorporate the shortening and the puncturing of the parity. That I will, like I said, will leave as an exercise for you to make a modification. It's not too difficult. The changes have to be done here and there. So here you can see the rate is 1, all the things were in error. So 0 dB EB over N naught is too low, 2 dB is pretty good, and 3 I'm sure will be even better for these kind of code rates. Okay, so that's the end of this lecture on LDPC codes, and with this we come to the end of the LDPC codes part of the of this course. So like I promised at the beginning of the course, you have an encoder for a code in the 5G standard, and you have a decoder also, sort of a working decoder. I'm sure it can be made better. There are lots of bells and whistles you can add, but it's a pretty good decoder. It's got quantized received values, it's running offset Minsum, and you can play around with these parameters to see how you can change and improve, etc. And some of this we will leave as exercises for you. Okay, so thank you very much. This also concludes the second week of lectures, and we will proceed to Polar codes in the next week onwards. Thank you very much.